my screen. Okay, so you've already seen today a good introduction to the GUI and how to build some models there, and then also an introduction to how to build some of these models programmatically. So what we're going to do today as exercises has a bit of both, and we're going to do a tutorial that is focused on oscillations and synchrony in the brain, a very simple network that has some oscillations, and just very briefly, synchronization of neural activity is a very common phenomenon, and it's you see it within and across brain regions. It basically refers to the very precise temporal coordination of different cells spiking at the same time. And it has been shown to have a role in many different aspects of brain function, from cognition, memory, perception, behavior. It's involved in different disorders like schizophrenia, epilepsy, tremors, and so on. So it's quite an important aspect. So here we see an example of neural oscillations and synchrony in the hippocampus. And these are different examples. As you know, the different oscillations are characterized by their frequency, from delta to theta, alpha, beta, and gamma, which are the fastest. And so what we're going to do today is just generate a very simple network that generates some oscillations, and we're going to try to then modify some of the parameters to alter the oscillation frequency. So we're going to start by doing this on a Google Colab, and I just shared on general the link to the Google Colab that we're going to start from. So if you can all open that and make a copy. So we're going to play around with this Google Colab, modifying some parameters, and then we're going to try to implement the same thing on the GUI. So you're going to take the lead on that, and I'll ask different people to try to implement this simple model in the GUI. So we have a bit of both, programmatic and GUI, and we'll see very clearly how they are related to each other. Okay, so everybody has this tooth oscillation Jupyter notebook open. Anyone having issues?
Where is the link to this, Salva?
Oh, sorry, it's in general, the general channel at the last message I sent. Oscillatory network tutorial collab.
You will be saving it to the drive as well, right?
Yes. So make a copy and save it to your drive so you can play around with it. And I'll also add it to the Google Drive. Yes. Save, copy, drive. Okay, so let's get started with this. So the first cell here is just the basic things to install Neuron, install NetPyNE, and these two lines to make sure that the figures in Matplotlib appear in the Jupyter Notebook in the Google Colab. So if you run this, you should just get the basic output. And what I've done next is copy the whole model, which is not really that long, in a single cell in the Google Colab. And the reason for that is that we can use this as if it was a script, a file in the editor, and just modify params here and just run. So we run a single cell each time, we modify, and we see the effect on it. So sometimes it can be, depending on what you want to do, a bit easier to do it this way.
This is much cleaner than the way we were doing it earlier, where we jump back and forth. That's a mess, and I don't recommend it.
So the model that we're going to start with is actually the tutorial 2 from the NetPyNE website, and it's a very simple network. So I'm just going to go quickly over it, and then you have some exercises to do here at the end, modifying some populations and adding a couple things to get oscillations in this network. So let me go over it. So first here at the top, we have the cell parameters. And I'm using kind of a slightly different method to define them, just to show you that we have the flexibility of NetPyNE dictionaries and lists. So what I'm doing is I first create a dictionary that contains just these sections, sex entry, and then I start filling in that dictionary. So I create a soma inside, and I make sure it has the geometry and mechanisms dictionaries that you will need, empty at this point. And I then, for example, fill in the geometry. So now I have this dictionary nested dictionary structure. So I go sex, soma, geometry, and I add these three values: diameter, length, and axial resistance. I then go on to mechanisms. So I use, again, the same hierarchical structure, the inside sections, the soma, the mechanisms, and I add this Hodgkin and Huxley mechanism. Okay, so see how it's slightly different from how we saw it before, which was the whole dictionary in one go with opening all these parentheses and closing. And here we're just doing it bit by bit, the same overall effect at the end. So we add the Hodgkin-Huxley, the 4 variables, and then what we do is add this variable, this dictionary, to our NetPyNE structures. So we have these netparams, cell params, which is where we store all the parameters of the cells, and this cell type that we're calling pyramidal, we assign it this dictionary that we just filled in. Okay. So moving on to the populations, now we're going to use the structure called netparams popparams, and we create a new entry for the sensory population that we're calling this model, S. It's going to be of cell type pyramidal, and it's going to have 20 cells. And we create a motor population. It's going to be cell type pyramidal and 20 cells as well. So we have 40 cells in total. Next, we move on to the synapses, synaptic mechanisms. So we use the netparams, synmecparams. We create one synapse called excitatory. With these parameters is X to syn as usual. Moving on to the stimulation, we're going to create a background as we had before. It's going to be a spike generator, so a netstim. It's going to generate an average of 10 spikes per second with a level of noise of 0.5, so kind of halfway random. And we're going to target all the pyramidal cells. So all the cells are going to have this background input. Yes, make sure it has the same nice structure. So the source is going to be the background. The conditions, so it's going to be that all the cell types of type pyramidal, weight 0.01, and delay 5 milliseconds. And finally, we have a connectivity rule, very simple, that goes from the sensory to the motor population. So the conditions of the presynaptic cells is that the population is S, sensory. Conditions of the postsynaptic cells, motor. And we're going to have a divergence. So this is something we haven't seen before. Let me just check. This is the original the way we start. If I type NetPyNE, you either get Netflix or NetPyNE. Depends which one you use more.
Netflix v NetPyNE is a constant battle on my browser.
Yes. Okay, so I'm following. Yes, I thought this was wrong. So actually, the value that we had in the original model was this probability of 0.5. So I'm going to change that back. So if you can do this with me, change, instead of divergence, have a probability of 0.5, what we had in the original tutorial starting point. I can also save this in case you want to make a copy from there. Okay, and then we just have the typical simulation configuration parameters. So the duration, integration step, what we want to record, the voltage. We want to save to a JSON file. In this case, doesn't really matter. We can set it to false because we're not using this really. And we're plotting a couple of things by default. The plot, the raster, the traces, and this new thing called the rate spectrogram, which basically takes the firing rate of different cells, bins them, and generates a spectrogram. So it tells you which frequencies are have more power in terms of the firing rate of different populations. And I want to show that for all the cells together, so combined spectrogram. Okay, so if I run this, then I get a bunch of figures. So first, well, we get all the information. We created a network with 40 cells. No connection, so that is strange. We should check that.
I thought there were connections. Go back down for a sec. Yeah, 203.
Oh, sorry, I read. Sorry, yeah, I read wrong then. Good. Oh yes, perfect. 203 connections. Good. I read node 0. Okay, and we have 243 and 900 spikes. So we see the output of the network. We have these two populations, sensory and motor. And can anyone figure out, based on the structure of the network we define, why the motor population, which is actually shown here at the top, is spiking more than the sensory? You can go back to the code and check the specifications.
Well, the connectivity is from sensory to motor, so everything gets stimulated by the stimulation source, but also the motor will also get stimulated by the sensory neurons.
Exactly. Perfect. So yes, we have background input going into all the cells, but then the sensory project into the motor, so the motor have a higher firing rate. Very good. So yeah, we can also see some of the voltage traces, the spikes of one of the cells, and this rate spectrogram, which really doesn't tell us much right now because we don't really have any strong oscillations. And so it's all over the place. Okay, so now let's go on to these exercises. So I'm gonna have you do until step 6. So 1 to 6, and then we'll stop and we'll see what's going on. I'm gonna read what we have to do, and then I'll leave you some time, and then we'll go over it. So start from NetPyNE tutorial 2. This is the one we have right now. And it says rename the M population to I. It's gonna be now an inhibitory population. Okay? And we basically wanna do this because usually to get oscillations, we require inhibitory activity. Then says add an inhibitory synapse called INH with the same properties as excitation, but the equilibrium potential -70. Increase the background input to 50 Hertz, but target only the S population. Okay, so that it gives you actually the code there. Let me just make this code friendly. And then it says add a spike histogram. So this is a new plot that you have to add at the end, and run the model. So let's have maybe 10 minutes to try to do this, 5-10 minutes. And I'll ask someone to go over it.
And feel free to chime in with questions or anything.
Yes, please.
I have one. I was able to get the code to run, but I'm not having any of the plots coming up.
Yeah, the same for me also.
Okay, so
That might be that
Same, same here.
okay, so make sure you run these lines at the beginning at the top.
Mm-hmm.
I had the same problem. If you take the percentage matplotlib inline out, copy it out, and then paste it into a separate cell and run it, it should work for you.
Oh,
That seems a little buggy, but weird.
I don't know why it did that.
Huh.
okay, so I think he's suggesting doing this.
Yeah, that worked.
Hey, excellent find. That's weird.
Very obvious solution.
I have a question.
Yeah.
So we add the synapse mechanism. Should we also add the connection from I to S, or we just add the mechanism?
No, not for now. We'll do that in a bit.
Sorry, I think I'm working with the wrong file.
Okay.
Where is the NetPyNE tutorial 2.py?
It should actually be this one that you're using. It should be tutorial the Jupyter notebook. So
okay, it's the same file.
The same one, yeah.
I see. Okay.
I copied from tutorial too.
You might have to save it to your own drive in order to be able to do stuff with it.
Sorry, in the cell connectivity rule, we have to change to I, not to inhibitory population, or not? Because
Which step?
No, not one of the steps.
Ah.
But in the connectivity rule, we should change.
Yeah, you're going ahead. There's one of the steps
Okay.
later on, I think, that does that.
Okay.
Okay, so I think we're almost, most of us are there. So maybe I'll do how I did yesterday and call out people, and I'll start at the back now. So Afarin Jalil.
Oh, yeah.
Hello.
Hi.
So you wanna like tell me the changes you made in the code? What changes you did? So for example, for step 2, rename DM pop to iPod. How did you do it?
Yeah. So you just need to change like where it says like population parameters M, you would change it to I.
You don't have your feet here.
Perfect. And the third step, add an inhibitory synapse called INH with the same properties. How did you do that? Or Afarin?
Yeah.
Yeah. Sorry.
Yeah, I'm here. So the equilibrium potential would be E, or it would be EL.
So we want to make a new synaptic mechanism like this one, like the E is XC, but instead of that one, we want it to be inhibitory, INH.
Oh, so then you would just change it to the name to INH and then change the parameter value.
Okay, so I make a copy of this one and NetPyNH, and we wanted to change the reversal potential to -70. So which parameter would that be?
It would be the E parameter.
Okay, perfect.
Yeah.
Thank you so much. Okay, so that's step 2 or 3. And now we want to increase the background input to 50 Hertz and target only the S population. So let me see who's next. Maria Popova.
Silva, one question.
Yes.
Won't we change like the way we have declared pyramidal cell? Shouldn't we declare something called like interneuron cells?
Yes, in theory, yes. But because this is a very simple model, we're just going to keep the same cell type for both.
Oh,
So,
okay.
Yeah, but yes.
Yeah, hi. So to make the rate 50, we should go to stimulation parameters and change the rate to 50. And then to create our new conditions in the net parameters, stim target parameters, we need to basically copy paste the line. So it would be conditions and then brackets, curly brackets, pop S. Yeah.
Okay.
Yeah. And maybe in synaptic mechanism, we probably also should write inhibitory instead if you use it.
Sorry, what was that?
In synaptic mechanism, here maybe we should write inh instead of exc because we use inhibitory synapse now.
No, but the one we're changing right now, this one? But you mean like our next step? Yes, so we're going to do that in a bit.
Yeah.
Okay, you're very advanced for this course. Okay, so next step is the add Spike histogram, which is already here, so I'm just gonna copy it straight away. And I'm gonna add to the list of analysis. Okay, and then run the model and let's see what happens. So I think you're already all pointing at the issue here. Okay, so we don't have spikes in the eye population. Why is this?
We changed the background to only go to the sensory population, so there's no input to the inhibitory population to cause spiking.
Okay, very good. Okay, so let's continue. And now let's just do the next.
Sorry, can I ask you something?
Yeah.
In STIM target params, if we want to target part of this S population or population, how can we do that? I mean, not all the 20 cells, but let's say 10 or 5 or whatever.
Which part are you interested in?
So, yeah,
I don't have something specific right now, but you know, I just want to know if we can do that.
Yes, so there's a couple. There's a couple of ways. So you could potentially use, if you knew the region within that S population, you could use things like I and specify a region from 20 to 50, and you could also use. I don't remember the syntax, but there is a way that you can, I think it's cell list, but I would have to check this.
Oh, okay.
And this provides a list of relative indices within this population that you want to target. I believe I will check that later and confirm. So you can do like 3.
Thank you very much.
1, 2, 3, or you could do something like list range 10 for the first 10 cells in this population. Okay. Okay, so let's just do the next ones sort of interactively. So let me see who's next here. I have oh, sorry, I missed a couple here. Heitor Sanchez, you wanna try number 7, which says change the connection S to M to S to I.
Okay. You go to cell connectivity rules. Change S to M to S to I. In the name, so it's just the name, right? And then in post cons, change M to I.
Perfect. So remember this at the top here is just a label. So it's an arbitrary label that doesn't have any functional meaning. And the actual thing that changes the connectivity is here in the population I.
Okay, change the comment too, but no.
Yeah.
No.
Okay.
No. Yeah.
Okay, and next step, it says reduce the S to I divergence to 1. So yeah, you wanna continue, Heitor?
Yes, you. So I believe you have to change probability to divergence.
Perfect.
And it equals 1.
Okay. So I don't think we explained this, but divergence is, if you imagine each presynaptic cell is going to diverge and connect to many postsynaptic cells. So divergence is the number of cells it connects to. And if you had convergence, that is from the other direction. So for each postsynaptic cell, you're going to have many cells connecting to it. So convergence is the number of cells that connect to each postsynaptic. And these values are also, they're implemented the connectivity in a probabilistic way. So the cells that get selected to connect to or connect from are random, but deterministic in the sense that we can replicate the experiment.
And you have to choose one of these, and probability overrides convergence or divergence.
If you had both, then you shouldn't. But if you by mistake you have probability as well, then probability takes the lead. But yeah, that's you should avoid.
Again, what divergence versus convergence is?
Yes. Let's see if I have a quick diagram. Convergence versus divergence. Not seeing any good ones. Okay, so just quickly right here. So if you imagine, are you seeing my PowerPoint? Yeah.
Yes.
Okay. New slide here. So you imagine a cell here, a presynaptic cell, and I'm going to put a couple of postsynaptic cells. 1, 2, 3. So divergence means the number of postsynaptic cells that each presynaptic cell connects to. So if for example, I had a divergence value of 2, that means this cell connects to 2 of these randomly. 1 and 2. Okay, this is a divergence of 2. If I had divergence 3, it would connect to all 3. If I had divergence 1, it would only connect to one of them randomly. And convergence is the other direction. So imagine I have a bunch of presynaptic cells. You can, of course, have a bunch of each. Then convergence is for each postsynaptic cell, how many presynaptic cells are projecting to it. So if I have a convergence of 2, then I will have inputs from 1 and 2.
So the probability won't have any direction, right?
The probability is a sort of a combination of these, which tells you out of the total possible connections, if you have 3 presynaptic and 3 postsynaptic cells, 3 by 3 is 9, so I have 9 possible connections. So if you have a probability of 33%, you would only have 3 out of those 9 connections. So it's out of the total space of possible connections between all pre and postsynaptic cells, how many of those are created.
So convergence and divergence parameters, they have to be integers.
No, you can, when you're defining connectivity, you should use only one of the 3, either probability, convergence, or divergence.
Right, but can convergence or divergence be an integer or a float?
Yeah, that's what I'm asking.
Oh, sorry.
A like integer value, right? Or can you have 0.5?
No, sorry, yes. Convergence and divergence are integers, and probabilities float from 0 to 1. Okay.
You cannot specify multiple, right? Like probability and divergence, right? Because you always compute probability based on convergence or divergence. There's only
yes, only one. And there's a 4th type of connectivity, which is it's called, let's see, I forgot the name, but it's something like custom or something like custom, where you
if you have all your own cells and you want them connected specifically, you can put in that specific connectivity.
Yeah, you pass in a matrix essentially with the pre and postsynaptic connections. Okay, so let's continue this. So we reduce the divergence, and now it says add a new connection I to S with probability 0.7, weight 0.02, delay 5 milliseconds, and inhibitory synapse. So let's see, I have Amanda. You want to give it a shot?
Yes, I went to the cell connective rules. I copied NetParams, comparams.
Very good.
Yes. And then I changed the first one from S to I to S.
Okay.
The first pre-cons pop, I put I.
Okay.
And the post-cons pop S.
Okay.
Probability of 0.7, weight 0.02. And changed excitatory for in.
Perfect. So we just created a new rule that is going to connect the inhibitory to the sensory population. And I think I have a little diagram of that here. Yes, so this is how we started. Here at the top, we had background to the S and the M, and the S projected to the M. We then replaced the M with an I, and we projected only from background to S, so there was no spike in the I. And now we have this. So we have background projecting to S, S to I, and I to S. Okay, so now we have this recurrent connectivity here with an excitatory and inhibitory population, which is usually what results in this kind of oscillations. So let's see what we have to do now. Okay, so the last thing we want to do is just add this little parameter here called sync lines to plot raster. Oh, I see a message. Great, thanks.
Salvador, before that, I have a question in the number 9. Can we have, it's okay to have for the connection of S to I, we have divergence and not probability. And then for the new one, we just created connection I to S and we put probability instead of divergence. Can we have both in the same?
Yeah, that's totally fine because it's like different sets of connectivity and they can connect differently.
Yeah, each connectivity entry in the dictionary must have its own probability, divergence, or convergence, but you can mix and match those within different connectivity rules, yeah?
So the last thing I'm doing here is adding this argument to the plot raster function. It's called sync lines true. So this just essentially draws a horizontal line at each spike in the raster. And so that is a useful visual guide to see where synchrony is happening. So if you see all the lines packed together, there's a lot of synchrony. If they're spread out, there's not much synchrony. Okay, so let's try to simulate now. Okay, now we get
what does it mean? I mean, this grid that we're seeing here.
This thing.
Yeah. How?
Yeah. So
how do
this
you?
is.
Yeah. Sorry.
So this is the raster plot, but it now has these lines that I was mentioning.
Right. Yeah.
So when the lines are closer together, here they're relatively close. You also have like a synchrony measure here at the top that says 0.7. That means there is quite relatively high synchrony. If we, for example, removed these inhibitory connections, we set the probability to 0, for example, and run again. We see that there is much less synchrony here. The synchrony score went down to 0.4, and the red lines are all over the place because the spikes don't really happen on top of each other.
I see.
Okay, so adding inhibition usually increases the synchrony. So you have this recurrent loop.
I see. Okay.
So in words, the red line means that a sensory and a motor neuron fired at the same time. Is that what that's? What does a red line mean in words?
The red line is simply where there is a spike. There is also a red line. So for each spike, we are plotting a red line on the raster.
Okay.
So if the spikes are sort of close together in staying the same vertical dimension, you will see them very close. So let me run again.
This isn't really an analysis as much as a visualization. We just draw a red line for each spike, and if we see white in between a bunch of dense red, we know we can visually see synchrony.
Is there any way we can measure the density of these red lines to check how close they
so
are
as I
to
mentioned,
this?
mentioned, there is also a synchrony measure here at the top of the raster, in the top right, and this is a very simple measure. I don't remember exactly, but it's essentially what you're saying, like sort of calculating how close the lines are together. How much?
And you can pick different subsets of cells and populations and measure the synchrony between those. You'll have different synchronies between different populations.
Yes.
Oh, okay. So what's the difference between the first red line and, let's say, the second?
It means that there's a different firing, like a neuron fired at a different time between these lines, right? So that's
every spike of every neuron draws a red line. So this is really just visual. It's like we're looking for places where there's not much spiking, where it'll be mostly white, not very red. And then there'll be places where it's dense red lines because a lot of spiking is synchronous there.
So if we count them, it will be hertz.
I'm sorry?
If we count them, it will be 16 hertz. Like, so it should be 16 of them.
Not, you're saying that because you see here 16 hertz at the top, but notice that is the average firing rate. And for each of these sort of blocks of activity of waves, there might be more than one spike. So you might it might not coincide with the average firing rate. So the best way is either to count the red blocks to see the overall oscillation frequency of the network, or what we're doing here, which is plotting this nice spectrogram, the firing activity, which is basically giving you the peak oscillatory activity of the network. And we see that it's around 30 hertz, maybe 29, 30 hertz. So if you actually counted the red lines, 1, 3, 4, 5, 6, 7, 8, 9, 12, 14, 15, 16. Yeah, so I'm about halfway through, and I have 15, 16, so that matches the 30 hertz that were shown in this spectrogram. Okay, so now the exercise is for you to try to modify some of the parameters in the network and get different oscillatory frequencies. And you should be able to get from very low ones, like 5, 10 hertz, to faster ones, like 40 hertz. Okay, so make a note of the things you modify, and then in a few minutes, I'll ask you to make some suggestions.
Silva, can you save that so that I can?
Yes. Save now.
Got it. And what about the other graph, like power spectrum and other stuff which you showed?
That should appear because it's here already. So when you run, you should get those graphs.
Okay.
So notice that there is two ways in NetPyNE to plot figures. One is including them in SimConfig. So this is, you know beforehand the things that you're gonna wanna see. So you just include it here in this dictionary structure format. Or once the simulation finishes, you can also just run, sort of using the API, any function you want. You want to say plot spike hist, for example. With the column. Okay. Or you can say plot spike statistics, which is a plot that we don't have. Stats. Okay, and you get this is the firing rate statistics for each population, and this is the irregularity, the interspike interval coefficient of variation. Okay, so let's try some things here. So, Carol Upchurch. Yeah, any suggestions how to change the oscillation frequency?
I changed the delay from 5 milliseconds to 1 millisecond, and that got me some faster oscillations.
Oh, sorry, I'm having trouble hearing you. The delay?
Yeah, I changed it to 1 instead of 5, and that.
Which delay? There's like
I changed both of them.
From the connectivity rules, you mean?
Yeah.
There's also a delay here in the, okay. From 5 to?
1.
To 1. Okay, let's see what it is. Okay, nice. So we got a much faster oscillation, 45, 50 hertz. Let's see. So interestingly, that doesn't really translate into more spikes. So notice that there is a difference between the firing rate activity of individual neurons and the overall network oscillatory activity, because this is composed of spikes from many different neurons and whether they are synchronized or not. So here we actually have less overall spikes, but they are more synchronized and they lead to this higher oscillation frequency. Okay, so and that was the delay of the connectivity. Okay, so I guess that kind of makes sense. Carol, how would you explain why the oscillation frequency increased?
I'm sorry, can you say that again?
So why do you think the oscillation frequency increased? So before we had 25 hertz and now...
So the communication between both populations of neurons should be faster.
Okay. Yeah, basically that's the idea. And we can see here in the voltage traces that it's not only the spikes that matter, but also these sort of non-spikes, which are the result of the inhibitory activity. So these are caused by IPSPs that prevent some of the cells from spiking. And they both happen very quickly, both the spikes due to excitation and the inhibition. So the interval between them is very fast now. There's only 1 millisecond delay. And so you get faster oscillation. Okay, something else. Let me see who's next. Monica Bell.
I reduced the connection probability of the inhibitory to the I to S connection. I reduced it and it increased the frequency slightly.
What value did you use?
I used, as opposed to 0.7, I used 0.1.
Okay. Okay, so we see here that really almost removed oscillations, right? Because we're seeing that there's not much synchrony in the network, so there's no real network oscillations per se. You can see that almost in the raster here in the spectrogram. We have a bit at the beginning, but the rest is a bit just noisy. Yeah, so maybe we can try different values there instead of 0.1, 0.3. See what does that. Okay, so that also removed part of the oscillations. They're much weaker, there's less synchrony, and it's more noisy. But we could say also that it increased a bit the frequency of oscillation, even though it's less clear. It's a more noisy oscillation. Okay, thank you. Next is Jose. Jose. Jose Mendez.
Oh, sorry, I was muted this entire time. So I was saying, if you change your inverse potential, I think it was called, from -70, to -20, you should get a bit more oscillations. And I think your synchrony is still like a 0.7 something.
Okay, let's check that. So that is kind of interesting change because it's really changing the type of synapse that we have. So it's really not clear now that it's an inhibitory synapse. So excitatories are about 0 millivolts, and inhibitory, they try to bring the cell to resting membrane potential around -65. And this one is somehow in the middle. So I'm not sure what kind of synapse that is, but it's interesting. And it does change the oscillation frequency of the network. It keeps it at a very clear synchrony level of 0.7. The voltage traces look weird because, of course, this new synapse that you created is trying to move the cell membrane to this higher peak, which doesn't really create an IPSP, but it prevents the cell from firing because it's in a very depolarized state. So yeah, you invented a new kind of network, and you brought the oscillation, the oscillation frequency down to 20 hertz, which is perfect. That's what we were kind of thing we're looking to. Okay. And any other ones, Jose?
No, I was just messing around with the weights and some of the other things as well, but it didn't really change anything too drastically.
Okay. Laura Medlock, do you have anything?
Yeah, so the only, other than everything that's already been said, the only other thing I played with was the inhibitory synaptic mechanism parameters, the tau2.
Perfect.
So I changed that from 5 to 1 to make the decay faster, and then you get less synchrony, but the firing, like the rate goes up.
Okay, perfect, yes. Yes, so you decrease the synchrony. Now the spikes are closer together, but you do still have some kind of oscillations. And you can see this, the power of the oscillation is in 40 hertz now, so it's a bit faster. And the spike histogram we're not looking at, but it also kind of shows you these peaks and whether there are oscillations or not. So good. Any other thing you tried?
And no, everything else has been said. I was just playing with the same weights and probabilities.
Okay. So I think another interesting one is if you go in the other direction. So instead of decreasing from 5 to 1, if you increase to 20, for example, you should get the opposite effect. And yes, we kind of get it. It's pretty strong at the beginning, at least. You have these very slow oscillations. So maybe 1, 2, 3, 4, 5, 6, 7 hertz or so. And you see that pretty strongly here, around 10 hertz is showing. But then it dies off. So there's like too few spikes to keep this going, and it kind of dies off.
Can you repeat what change was that, please?
This was the tau2, the decay time constant of the inhibitory synapse, from 5 to 20.
Thanks.
Try 15. Yeah, so if I try 15 hertz, sorry, 15 milliseconds in the inhibitory synapse, where is it here? Tau2 inhibitory synapse, 15 milliseconds. So basically, that increases the synchrony quite strongly to 0.8, and the frequency goes down to around 18 hertz.
Sorry, can you please explain again why this is happening when we increase the tau?
Yes. So anyone wanna give it a go?
Sorry, the synchrony goes down, right?
The synchrony goes up, the level of synchrony, which is a measure of how much the spikes are aligned. Yeah.
Yeah, no, I just got it the other way around.
and the frequency goes down to 18 hertz. Anyone has an intuition of why this might be happening?
I think it might have to do, I mean, correct me if I'm wrong, if you have a larger time constant for tau2 is the decay time constant.
Mm-hmm.
So if it's larger, it takes longer for inhibition to wear off. So there's more of those gaps, those like no spiking gaps in between where the synchronous events are.
Yes, exactly.
Okay.
Perfect. Yeah. Yeah. So these. Yeah. Go ahead. Okay. So the inhibitory neurons are providing inhibition to the excitatory neurons. And if you increase the tau2, it means that this inhibition decays more slowly, so has an effect on the ability of the excitatory neurons to spike for a longer time, so they cannot really spike again until this inhibition decays completely. And then you get another spike from the excitation, and the whole process repeats. Anyone else has any other interesting combination to change this? Yeah?
I think I got one.
Okay.
I changed the delay of the connectivity parameters, the inhibitory one from inhibitory population to the sensory population, the delay to 20, and the weight to 1.
And the weight.
And I get something similar to the.
Okay, the weight to
1.
To 1.0 or 0.01?
1.
Like a
1.0.
Oh wow, that's very strong. Okay. That's it. So this is for the inhibitory receptor. Okay. Yeah, so that's nice. So we have.
It's like a slow oscillation.
Very strong.
Very slow oscillation.
Yeah, like a 10 hertz oscillation and very strong because you have made the connections very strong from inhibition to excitation. So the synchrony is quite strong.
Inhibition.
Yeah, very good. Okay, so any other suggestions?
Do you hear me?
Yes.
I tried to increase the divergence from excitatory to inhibitory.
Okay.
For example, put it 5 or 10.
Okay.
And it will make the oscillation stronger.
Okay, nice. Yes.
So it increases the synchrony. And interestingly, when you change the weight from the excitatory to inhibitory, it increases the overall firing rates, but it does not change oscillatory properties quite much. So
what did you use? Twice, for example?
I tried wide range. You could try 0.1 or 0.2, and it does not change neither frequency nor synchrony, I would say. But increasing the divergence would increase synchrony.
Yeah, so why do you think that is, that the weight doesn't have such an effect?
Yeah, about the divergence, it is quite clear because you have more like overlapping between inputs from different cells, and of course the network becomes more synchronous. And about the weight, I'm not sure actually. It increases both rates, I guess, and it stays quite balanced. I don't know. So
yeah, my hypothesis is that the previous weight. Oh, David. David, did you want to say something?
No, sorry.
Just share your music, okay? So my guess is that it's the previous weight is already pretty strong, so the overall effect is the same. So it's going to generate a spike even if the weight is above a threshold weight, you're gonna generate a spike in any case. So there's no real change to what the network is gonna do.
But could you try to increase it even more, because it really has an effect on the firing rate. It was like 20 something, and now
no, maybe I overdid it.
Yeah, okay, it's too much.
Oh yeah, the firing rate goes
2023, try 0.2, for example. I think it's not too much.
So I guess in a way it is actually recruiting more cells.
Again, so okay,
but the cells are doing the same function. So the oscillations can be generated by 10 cells of each population or by 20. But if those cells are firing at the same range of times, then the overall network oscillation is gonna stay similar. Like here we have, the firing rate is higher because more cells are firing, but they are all firing within these small ranges of the red lines. So the oscillation that results in the network is similar. There's no variability.
Yeah, could be.
Okay, any other questions, comments?
Yeah, I have a question. It looks like all of the delays are always like set to a specific number for all the connections, and I was like playing around with adding some randomness in the delays, like adding a normal distribution, just to see like if I can break the synchrony. I'm curious, like how does NetPyNE like work with, like, does it generate a number and then it reuses that number over and over again for the same connection, for the same delay for that connection? Or each time the cell is getting fired, there's like a different delay based on that normal distribution?
It's gonna be a fixed delay for each connection. So when the connections are created, they get assigned a random value that is used throughout the simulation.
Makes sense. Yeah.
So what did you get with that?
I just try to like change the standard deviation so that like if I increase the standard deviation of the normal distribution, it starts breaking the synchrony because the delays are like off time. But if I keep it like standard deviation 0.2, it doesn't really break. So yeah, I just played around with all of them.
Okay, so I just tried some values. What expression did you use here?
I did normal.
Okay.
Normal. And then I think you're missing a parenthesis.
A bracket, yeah. Okay.
Bracket.
And what values did you use?
5 and 0.2.
In both?
Yeah. Hello.
Okay, so not
too
much enough an effect, but if you increase this. Yeah, you lose a bit of synchrony, but it's not.
It's also the stimulation has a constant delay, so that.
Yeah. Okay.
Can I ask a quick question, Sala?
Yes.
So
yes.
So if you wanted to vary the delay, if you wanted to add some random noise to the delay on an individual individual connection during the simulation run, how would you go about doing that?
Ooh. so that the delay of that connection changes every time. I'm not sure if that is possible, unless you actually do some modification of the network during the simulation, which is possible. So there is a function in NetPyNE called run with interval function or something like that. So it runs and stops at a interval that you set, and you can do modifications to the network. So for example, I use it to simulate changes in some parameters of some ionic channel to simulate, for example, neuromodulation. So you can basically change any value of the instantiated network and then continue running and do this at intervals. So you could potentially change the delays of the netcons, but I don't even know if that is allowed in Neuron.
So if you wanted to do neuromodulation like that, you'd have to do it you'd have to model it by stopping.
Yes, I mean, you can have neuromodulation as maybe you can have a separate population that simulates some inputs from a neuromodulatory region like locus coeruleus and provides inputs to the network ongoing. So you wouldn't have to stop. It would just be like another population of cells that provides some kind of inputs and modifies the network dynamics.
Okay, yeah.
Potential. But if you wanted to change conductances of some ionic channels, then you would need to do it this way. Or you can actually provide from the beginning. Actually, it's possible to do what you want with something called playing a vector into the parameter value. So the netcon delays, you can use this thing called vector.play and set a set of values at the beginning of the model and then play that into the parameter that you want. It's a bit more advanced. You can do it in Neuron. But yeah, that's possible. If anyone is interested, I can show you examples. And you can also use this, for example, for playing a time-varying current that you have recorded or whatever into your simulation. You can do that as well. You can play it into the I clamp amplitude, and the current clamp will change over time.
How would I call vector play if it's in Neuron?
I don't remember exactly the syntax now, but it's creating a variable of the type h.vector, and then using the play method. So the name of the variable .play, and I think in brackets you put the target or something like that. I can, if you remind me on the Slack chat, I can give you examples. Okay, so we have around 45 minutes left. So I know we're all very tired, so we're just going to finish off with something which I think is relatively simple. So we're going to go back to the GUI, and what we're going to try to do is implement this same example using this Jupyter notebook as a reference in the GUI. Okay, so we're going to create the populations, create the cell types, all slowly, step by step, and we're going to try to reproduce the same oscillations that we're doing here, but in the NetPyNE GUI. I'll give you a couple minutes to get set up. Hopefully the GUI is working now. And then maybe we can do it sort of interactively, and I can have some of you just share your screen and show how you are adding these populations and the different components. I'll give you a couple minutes to get ready.
Okay.
If you already have the GUI open, but you have something there, make sure you clean it. So go to File, New, or Clear. Okay, so the idea is that we all follow along, and I'm gonna stop presenting, and I'm gonna ask Claire Short if you wanna volunteer to share your screen and do adding the first population or the first cell type.
Okay.
You can share your whole screen or just share a window.
Okay, I almost got it. Okay. Okay. I had some issues with my notebook, but I think I should still be able to do that. Okay. So would I be starting with this piece?
Yeah, so let's try to add this new cell type called peer, and you have there the parameters. And everybody, let's try to follow along. So
would
probably
this
this is an empty cell, yeah, because yes,
okay.
So we can start from scratch.
Okay.
Okay, so we have one section.
Would that just be Soma and?
Yeah, just Soma.
Yeah. Okay.
Okay, so we have added one section and we rename it to Soma.
Okay. And do I have to change it here then?
Yes.
Yeah. Okay. 18.
So we set the diameter to 18.8. Length to 18.8.
Oh, shoot. Oh, okay. Okay. Cool. And then move to the next one.
Yes. So yeah. So you have the geometry now. Did you enter the capacitance? Oh, you didn't have it, but it's gonna use default. That's fine. Okay. Yeah. So you can move on.
Okay. Cool. And then is that a whole nother cell or another section?
No, so it's actually, if you go back to the code, so you see it says mechanisms. So what you have there is the HH mechanism inside the Soma.
Okay.
So you're gonna add a new mechanism, which is the little, yes. Perfect.
Okay. Oh, okay.
I can tell you the values.
Okay, thanks.
0.036.
Oops.
The DL is 0.003 and minus 70.
Cool.
Okay. Great. So we're done with the cell. Very good. So yeah, I'll get someone else. Thank you so much, Claire.
Thanks.
So let's see. Oh, the order changed now. Philippe Schlegel. Philippe, are you there? Maybe not. Sonia Ruggieri.
Yes.
Okay.
Just a second.
Okay.
Okay, so you can see my screen, right?
Yes.
Okay. Yeah, so I'm sorry, I'm just one monitor right now, so I don't have, okay. Maybe I can reduce this one.
Not perfect.
And should go, okay, good. So we put all the mechanism, and now we should add, okay, the population. Actually, I think I already did it, so I'm sorry.
Okay.
Okay, so I add to population. The one I changed the name and I called S. Selected the cell types, and the number of cells is 20. And yeah, I didn't add any special distributions rules for left cell list. And then the same for the inhibitory population. So I parameter cells, number of cells 20.
Fantastic.
Okay.
So I hope everybody saw that. So I'll give a minute for everyone to add the two populations, S and I, of type peer, and 20 cells each. And maybe since you were so quick, you can do the next one too.
Yeah.
Okay, already done.
Okay, for this one, so I included the the excitatory and the inhibitory synapse. So I called the first one X, and then by selecting X to scene, I had access to the 2-time constant plus the reversal potential, and I think I put the right numbers in. Hope so, at least. Okay.
Very good.
And then for the inhibitory synapses, the same. So the name would be in. Mechanism always X2 and if I'm not wrong, the time constants should be the same, but the reversal potential minus 70.
Yes.
Perfect. Okay, perfect. Yeah, I stopped here.
Okay. So everybody is keeping up. We have the populations and the synapses. Let me give a few seconds. Okay, and yes, I'll get the next one. Thanks so much, Sonia.
Thank you.
Ramohan, do you wanna give it a go?
Yeah, I can go, but the only thing is I refreshed it, so I'll have to start new.
Well, yeah, okay. Maybe you can just show us this stimulation, and then you can fill in the rest.
So that's what. Can you guys see my screen?
Yes.
So yeah, that's what I was telling. I started
Yeah, so you don't need to fill in everything. You can just show us the next one that we are missing, which I think is the stimulation. And then maybe afterwards you can fill it in for yourself.
I mean, I'll have to create a cell though, right?
No, you don't need. You can create the other things. Oh, yes, sorry, because you need to select the cell. Yes. Okay, so you can do that. Yeah.
I can start with an empty cell.
Yeah.
Add section. Let me.
Actually, that is the name of the section, so that should be Soma, and there, yeah.
This should be cell, right?
That should be peer, yes. Peer for pyramid, yeah. And inside the section, you already have one. Okay. Now you have two sections.
Then, oops.
So you can actually fill this in afterwards. Now you have the cell, so you can use it. So let's maybe move on to the stimulation sources, if possible.
Stimulation source. Wait a minute. So that will be parameters, simulation parameters. If I this one.
This one, yes.
And then simulation source will be. NetSim is okay. Rate is 50.
Yeah, so you have to change also the name at the top. It's called background BKG. Okay.
And interval between spike is what is called like.
That is optional, so you either choose firing rate or the interval, so you can leave that one in blank.
Okay.
And you can actually, yeah, you just need to fill in the noise at the end, which is 0.5.
0.5.
0.5.
Oops.
Yeah, perfect. And now the stimulation targets.
Simulation target means source is PKG. Simulation condition weight is 0. Target location.
So we just need to fill in the weight, delay, and synaptic mechanism.
Weight is 0.01. Delay is 5, as I see in my screen though. Number of synaptic contact per. That's it, right?
That's it. The synaptic mechanism. You have to select target synaptic mechanism above.
Say that again.
Above. If you go up, the one that says target synaptic mechanism. Below. No. Below. That one. Yes. Oh. It got angry. Okay. Oh, I think it didn't like that. Oh, sorry.
Is that because I don't have the cell created?
I think it's because you wrote something in target section and then you removed it quickly and changed or something, and it felt kind of. So try writing something there. Try writing Soma. Use the same spelling you used before, which I think is all small caps, maybe. Okay. Oh, and yeah, okay, no, the problem here is that we didn't define the synapses, yes, okay. Okay, so we're good. You just need to define the synapses and then come back here and select the excitatory synapse.
So I'll go back here, right?
Yes. So, but we are good. We're gonna move to the next one.
Okay.
Thank you so much.
Thank you.
Okay. So you wanna stop sharing? Ramahan, can you stop sharing, please? Thank you. And
I stopped, right?
can you mute Ramahan? And can we have who else is here? Oh, Javier? Javier?
Oh, sorry, I just was talking. Just following because I'm fried. My brain is completely fried right now. I'm sorry.
Do you wanna skip?
Yes, please.
Okay, no worries. So we can have what else is here? Sebas?
Actually, I'm from my cell phone right now because I have trouble with the Wi-Fi.
Okay, no worries.
Yeah, I'm listening and trying to catch up with the
okay.
cards.
Sounds good. Maybe any volunteers?
I can do it.
Okay. That's David. Okay.
This is for cell connectivity rules.
Okay. Can you share your screen?
Yes. Present. So I created two connectivity rules, one from S to I and one from I to S. For S to I, it had a synaptic weight of 0.02. It had a divergence of 1 and a delay of 5 with the synaptic mechanism of EXC.
Okay.
And then the conditions were the presynaptic was from the S population, and the postsynaptic was from the I population.
Okay, good.
And then for the next connectivity rule, it was again a weight of 0.02, but this time it would use probability connection, which is 0.07, a delay of 5, and the inhibitory mechanism.
5 and inhibitory, and this is called I2S.
Yeah, so the presynaptic is the population I, and the postsynaptic is the population S.
Okay. Okay, and I think I just remember we didn't set the conditions in the stimulation target. So can you show us that quickly? In the background to pyramidal in the stimulation targets, outside of the connectivity rules, the stimulation targets.
Simulation targets.
Yes. So this one. Yeah, if you go to conditions, because I think we didn't set it before. Okay, so that should be target population
is S.
S. Okay, perfect.
Okay.
And I think we are just missing some of the simulation configuration for the plots, but I think we're good and we should be able to run already and see something.
I did the plot raster.
Okay.
Too. I just added one, and then it lets you pick raster, and then just clicking synchronization lines.
Perfect. Yeah. Okay. So we can do that. Raster plot and synchronization lines. Okay. So let's create some. I'm just gonna share my screen. Well, let me try first if it works. So I have some error. So these tutorials are actually already implemented. So if you go to the menu tutorials, simple oscillatory network, you will get this already working. So let me do that and share my screen. So, I don't know what happened there, but I basically just loaded the tutorial here, simple oscillatory network. So I'm gonna try and run. Okay, so the network is not very pretty because it's single compartment neurons. Actually, if we color it, it's a bit more pretty. And let's run the simulation with the rocket. Okay, so now it's finished, and now we can plot some of the other traces, I think. That's the plot and traces. We're not seeing the synchrony lines. Let me see the spike histogram. We can kind of see it here. And notice that the GUI doesn't include the spectrogram for this firing rate, but we can still get it using the Python console. So we can come here and say sim. Let's see. What is this? From NetPyNE. Sim, I think. Sim data analysis. Plot rates. Spectrogram. I think this should work. I think maybe we have to do this thing of the inline plotting. Lib inline. Maybe so important. Yes. Okay. So we can see now these frequencies. It's plotting for all the different populations. So I can just say here include, and I just want to include one population, which is all. Oh, okay. Okay, and we get a similar plot to what we were seeing before, oscillating at 25 Hertz or so. So if we wanted, we could go back, change one of the parameters. So for example, in the connectivity rules, you see, I have here some values. If I change the probability to 0.9, probability to 0.9, and I change the tau to 20, that should generate something slower oscillation. So I can run the simulation. And we can plot the raster plot. You see there are less spikes here, and if we just run this code again, oh shit, no, I deleted it. Oh, okay, not plotting line, import matplotlib, and dot analysis plot rate spectrogram trophic equal 1 and include equal off. Run this. Okay. Well, not really what I expected, but it changed the frequency somehow. So just to show that we can play with the parameters and change the oscillation frequency as well here in the GUI. And I think we're gonna conclude here. So do you have any questions?
A simple question. When will be the time to use the GUI instead of just using the editor?
Daniel, I see you're speaking, but I can't hear you. Oh, wait, sorry.
Can you hear me now? Yeah. When will be the time to use the GUI instead of the Jupyter Notebook or whatever collab? And now you're muted.
Yeah, you're muted, Salva.
I think the GUI is useful for beginners. So when you're learning, it's useful to know the different options that you have that you can do in NetPyNE. And it's useful to sort of sketch new models, simple models from the beginning, just to try out a couple of things in a small version before you export it to a script and then do more complicated things. And it can also be useful to visualize existing models. So you can import a model that you have developed, and it's sometimes easier to see, like the list of populations in this format here graphically, to click around and see the different options. Yeah, so for very, very complicated and large models, obviously it might not be ideal. Also because you cannot probably run them, it would take very long, so you need to use supercomputers and so on. But for prototyping models, I think it can be useful. Any other questions? Okay, so thank you so much, everyone, for staying the whole day. I know these are long sessions. And I'll see you all guys tomorrow morning. So tomorrow we're going to do some more NetPyNE and a bit more in-depth look at some of the features in NetPyNE.
Thank you.
Right on.
Thank you.
Thank you.
Thank you.
Thank you.
Thanks a lot.
Bye-bye.
Bye.
Thank you.